face recognition?
No, just my own human, yeah, don't worry.
The old way.
Yeah, the old way. So let's continue. So we were here. So we kind of threw the stuff at the k-means clustering using this machine learning pipelines, which are completely scalable. So you could have a lot of songs, more than 1 million songs. So let's sort of stare at this scatter plot, right? Because we know we don't know what the true clusters are for these songs, so we're just sort of exploring in this unsupervised land. And then what we start plotting here is simply so if you look at the plot options, I now have my loudness, tempo, and duration as values and prediction as keys. And I've chosen scatter plot as the display type, right? This is a pairwise scatter plot. So, this is basically the same table data. And if you look at the two clusters, along this coordinate, it seems like they are pretty reasonably split. So tempo versus duration and loudness versus duration. But then loudness versus tempo, you see there is like a mixing, right? So, so maybe let's explore this a little bit further. I mean, there's an overlay of both clusters. So if you believe that loudness, tempo, and duration are sort of minimal features that are representative of a song, then this is not an ideal clustering. So, well, okay, most of you know what a Euclidean space is. So this is what our loudness, tempo, and duration live in these three coordinates. And this is sort of the origin 0, 0, 0. And this is basically what we're trying to visualize the points in. So there is very little separation in the sense of having 2 point clouds. So at least along a particular pair of coordinates. So then what we can do is, so these are called sort of pairwise separation in sort of 2D projection of all 3 features in the 3D space. So I have points in 3D, they're colored whatever, yellow and blue. And then what I'm basically saying by 2D projections is I can project the points, 3-dimensional points, like shining light this way, and they only fall on this wall, right? That's one particular pair of coordinates, and this wall, one particular pair of coordinates, and bottom, right, another pair. And that's what the scatter plot is showing us. It's those 2D projections. And so we want to try to investigate why this smearing is happening across clusters. Okay, so if we sort of look at the transformed, we sample 10% and select duration and prediction. We see these density plots, so these are just histograms. And we can start noticing that, what this is, one of them is a skewed feature. Right? So do you notice, so duration, when you sort of look at cluster 0 and cluster 1, there are a lot of skew in 1, right? So this is kind of a basic insight, and you can say maybe I should plot in a different scale, not on the native scale of duration, maybe. So we could look at log duration, right? So how do we do that? We simply say table songs table. This returns a data frame, and then I'm using my select expression method for the data frame. So I choose tempo and loudness, but then I choose log duration. Log of duration as a new feature, and I call that column log_duration. And now I create my training data too, which again is a new vector assembler with input columns as log duration, tempo, and loudness, and output column as features. And then I want to apply this transformation to my original data frame. So now we create model 2. Model 2 is new k-means. Once again, we only have 2 clusters, and we want to fit the training data set 2 now. And then we also want a prediction. So we have transform data to transform 2, which takes model 2 and applies the transform method on the training data 2. And then we only select log duration, tempo, loudness, and the prediction column from the clustering. And then we're simply displaying a transform 2 at 10% of the sample. Right. So now let's see. So we have, so these specific ones, this pair and this pair are good, but this gets, so log duration and loudness gets mushed up. Okay. But this is all heuristic, right? I mean, so the songs with high tempo and loudness are put in one cluster, and song duration does not affect the song categories. This could be a conclusion, maybe because people in the 70s were just listening to long songs or whatever. So, I mean, the point of this exercise is just to show that what you feature engineer into the k-means algorithm is going to affect what clusters come out, and what you feature engineer is going to be based on domain knowledge, like what you think is reasonable. And the point is not to have everything in like its own color and all of this, and that's a different problem, especially with just 2 clusters. Yeah. Okay, so I started this thing, but forget about this. I think I explained this Euclidean space thing already. But if you want, there is this co-calc, just collaborative calculation in the cloud, which is a Sage Math environment. So we will use the same Sage Math environment locally for the foundations course, 04 later. Okay. Yeah. So the moral of this is you need to be able to tell a sensible story to your with your data science process to whoever is your line manager. So this is so people in the industry know this. So this is a delicate thing. So it's not about just finding the most complicated model. It's actually being able to explain the model to someone who does not need to know the mechanics, and it has to make sense to typically a manager in a product manager, whatever, in the industrial setting. Okay, so now let's get into the, so I want to kind of tell you one example of supervised clustering with decision trees. So we did unsupervised clustering, or we can call this supervised classification. Yeah. So here, I'm going to first start out by doing a visual introduction to decision trees and application to apply this to this handwritten digit recognition problem with grayscale images. Which is again a classic data set. So I don't want the underlying example data sets to be complex or the methods to be complex, but once again, this is a basic methodology you will study in a machine learning course, right? So did you do Thomas Schoen's course or in IT or no? Where did you take your machine learning course?
Well, I took it at IT, but it was a summer course.
Oh, it's a summer course, okay. I think it's the same one. I used R.
Yeah, it's cool.
Yeah. Okay, so has anyone taken Matteo Magnani's data mining course here? Nobody? All right, both courses I think cover this stuff in different styles. But let's kind of make sure everyone's on the same page. So I want to start with this visual description of I know people in my course have seen this before, but have you guys seen this visual introduction to ML? This is really good, right? It was done by some grad student at Stanford, I think, and some data artist in New York. So it's really beautiful. So this is essentially, so you can kind of slowly keep scrolling. So it's a data set about homes. And we're going to create a model to distinguish homes in New York from homes in San Francisco. So first, we're going to get some intuition. The homes in San Francisco are green and New York are blue. And what we're seeing is elevation. Where is the home above sea level? So San Francisco home, highest one is 744.8 feet above sea level. New York is 239. Okay, so New York is closer to the, well, yeah, it's flat. So it's so we're capturing the landscape a little bit. That's one of our features. Now we're going to add some nuance. We're going to go to another dimension. So we keep the elevation, but we also keep the price per square feet. So that's the second dimension that's coming in. Okay? It's the same homes. We just now have two dimensions. Price per square feet on the x-axis. Okay. Dimensions, the data set are called features. Yeah, so that's the language we're going to use. So now we want to start drawing boundaries, trying to split them into partitions or blocks, such that each block contains the same city homes, right? So this is kind of a greenish block, and this is kind of a bluish block. So New York homes are generally more expensive and are closer to sea level. San Francisco homes are, I guess the price drops per square feet if you go higher and higher up, right? In San Francisco. But here we still have both blue and green, right? So we haven't. So this is some way of. So what you do is actually use a tree to decide how to do the split. So you can think of one split as saying elevation is more than 73 meters. I guess that's this one. And the price per square feet is greater than 199, right? That's this one. So you split first along this way. That's why all of this is green. And then, so that's a branching tree in that axis with that Boolean, left or right. And then the same or above or below, and the same, but we only split the second, this rectangle into this part and that part. So yeah, so now we're going to start looking at this. We're not just looking at two, we're looking at 7 different dimensions simultaneously. And so this is the scatter plot matrix of all the 7 features: elevation, year built, number of bathrooms, number of bedrooms, price, total price, price per square feet, and square feet. And the elevation is still on the top. Okay. So we want to somehow use all these features to build some kind of a tree, this kind of partitioner of greater or less than in each dimension. And that's basically the decision tree. Yeah, it looks at one variable at a time and in a reasonably accessible manner and interpretable manner. So you can easily say, well, these homes are above this elevation and below this many number of bedrooms, whatever. Okay, so that's the plan. So how do you find better boundaries? So let's revisit the 73-meter elevation boundary proposed previously. So we can do the following. So if you flip it like this, so by transforming our visualization into a histogram, we can better see how frequently homes appear at each elevation. While the highest homes in New York is 73 meters, the majority of them have a far lower elevation. So your first fork or branch in the decision tree uses an if-then statement to define patterns in the data, right? So if a home's elevation is above some number, then the home is probably in San Francisco. That's kind of the logic or probabilistic reasoning. So in machine learning, these statements are called forks, and they split the data into 2 branches based on some value. So the value between the branches is called a split point. Homes to the left of the point get categorized into one way, while those on the right into another way. A split point is the decision tree's version of a boundary. Okay. So now, if we do this, a particular split point at 242.8 feet, then we say everything to the left is New York and everything to the right is San Francisco. Then we put 92 San Francisco homes in the New York pile, right? So, and then it's nice that 0 New York homes are in the San Francisco pile, but we only get 63% of all homes correct. So the trade-offs are the following, right? You pick a split point. Picking a split point has trade-offs. So if our initial split is say minus 73 or approximately 73 meters, then you classify, homes of one type into another, right? So then, if you move all the way to the 0 and say, everything above is, it's so so you have these notions of false positives, and so for example, here, if you look at the large slice of green in the left pie, those are all San Francisco homes that are misclassified, right? Because so these are called false negatives. I don't want to get you guys too bogged down with all the false positives, false negatives, and all of this terminology. Just keep that sort of at bay, because a lot of this doesn't work in every situation. So, however, a split point meant to capture every San Francisco home will include many New York homes as well, right? So these are generally called false positives. So then the best split point on this sort of line of reasoning, the results of each branch should be as homogeneous or pure as possible. So that means there are several, that means it must be as green as possible inside one and as blue as possible. And there are ways of measuring these notions of purity, right? So we won't get into those details, right? The Gini impurity index is a standard one for those who know what it is. But that's the intuition. Okay, so as we see here, even the best split on a single feature does not fully separate the San Francisco homes from the New York homes. Well, that's not going to happen, right? So you can get it 82% correct by sort of sliding around and finding the best fit by maximizing purity, some measure of purity within each side, each cell. But of course, we have 6 more dimensions, right? So here is the basic idea of recursion. So to add another split point, the algorithm repeats the process above on the subset of data that fell into the left or the right branch, right? So this repetition is called recursion, and it's a concept that appears frequently in training models. And that's exactly what we're going to do now. The best split will vary based on the branch of the tree you're looking at. So if you first split by elevation, you're going to get a best 82% correct. And if you split along the number of bathrooms, you'll get some other number and so on. But you can look at all of them, all the split points, that's what this plot is showing, and then find out, so for lower elevation homes, price per square feet is 1,000. It's the best variable for the next if-then statement for higher elevation. So you would always, one algorithm is just greedily choose the best dimension and the best point along that dimension to split to maximize purity. So that's kind of what's going on here. So you're growing a tree now. So you split by elevation first, and then you split by square feet on this side, but on the right side you split by the total price. And the forks of the tree keep growing, and you still use this purity maximizing heuristic to make the choices where and which coordinate to split. And as the tree keeps getting deeper and deeper, our accuracy is improving. Now it's at 96%. Right? Of course, if you keep going all the way, every home will be in its own cell, right? Or you'll reach a point where all the homes will be of the same color. Right? So that's 100% accuracy. Okay. So we'll come to that. That's basically overfitting, because then you fit all of your data. But before that, let's say we build that tree with 100% accuracy, and then we make predictions. So now the homes are falling from the top, right? And as they fall from the top, they're just falling into their left-right branches according to the price or whatever bathroom and elevation. And what you're seeing is that if we simply take this tree that's fitted to the data and pump the data back into the tree, you're going to basically see what you did, right? So it has 100% accuracy, but then the problem is, this is a supervised learning problem, right? So we're now moving away from this k-means thing, because these had labels called San Francisco and New York. So now if a home comes in without the city label, the question is it, and let's assume it's one of the 2 cities that the home is coming from. Then the question is, you have to guess with a high probability what it is. That's basically classification. So so to do this on a previously unseen data, we we have to, yeah, so ideally the tree should perform similarly on both known and unknown data, right? So you want to somehow train the tree and hold some of the data back so that, you know, when you test it on this held out data, it performs well. And this is called generalizability, or avoiding overfitting. Okay, so that's basically what's going on. And what I want you to pay attention to is that there are lots of tuning parameters here. So, and this is incredible animation, right? You can track the exact path that comes through. And so this is why I sort of said I'm not going to write notes and slides. And please go and give them a love. You know, there's a little whatever. Let's see if anything has changed. They said they'll do more stuff. Oh, okay. So anyway, there is a R2D3 team. Coming up next. Anyway, I haven't seen anything from them. Busy doing their PhD or something. So, what I want you to pay attention to is that one of the parameters you see when we completely fitted the data, what were we doing? We were just cutting wherever we wanted, right? We were just forking like crazy. So that means one of the parameters that controls the complexity, or how, you know, yeah, this tree is how deep you go, right? It's the maximal depth allowed in the tree. So you see here the maximal depth is here, right? So you split 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's kind of one way of saying this is a complexity class, right? So you may want to, so this is something later on we will do with the second type of held out data called the validation data, which we will use to actually change the depth. You know, choose depth 2, 3, 4, 5, whatever, and then for each depth we will see how well the test data. Sorry, you know, we will see how well it performs on the validation data, and we will use that to not like, you know, to control this hyperparameter called the maximal depth of the tree. And each model comes with its own tunable hyperparameters, which generally are about increasing the fitability, how complex the model can be. And so yeah, so that's basically decision tree, supervised learning, blah blah blah. Okay, so now let's take this a decision tree and then sort of speed up into. I think we're out of coffee, Simon.
Maybe tea?
Yeah, maybe. Okay, that's good. Okay, so and you know, we can just dive into Wikipedia for a lot more details. So the data we're going to use is this thing that everyone uses all the time. It's called MNIST, Handwritten Digit Recognition Data Set. It's from this paper, 1998. Our goal is to take this data and learn handwritten digits and learn how to recognize digits 0 through 9. Okay, and this is clearly a classification problem because we have only discretely finitely many labels, right? 0, 1, 2 through 9, so 10 labels. Okay. So now, what should be the takeaways at the end of this? Decision trees take several hyperparameters which can affect the accuracy of the learned model. There is no one best setting for these, and so we may have to do our own hyperparameter tuning in general.
What do you mean by hyperparameter?
So the hyperparameter in this specific example we might be looking at is maximal depth of the tree. So if you increase the maximal depth to 800, then you can fit a lot of data, right? So it's, so yeah, I mean, it doesn't have to. Yeah, I don't want to overemphasize hyperparameter. It's just some lingo people use. These are knobs you need to tune to make sure that your algorithm generalizes to unseen data. So it's this trade-off between overfitting and generalizability. Okay, so So here's the basic data set. So this is the handwritten digit 4, and there are others like 4, 1, 3, and so on. So, so this is stored in this popular libsvm dataset format. So we're not doing any, it's all pre-clean data like a standard introductory machine learning course. So we're not doing any ETL. So this thing is the training data. So it reads from Databricks datasets. I hope it still does. And then there is the test data, which is and I'm choosing, and I'm caching them, and let's see if this works. Does this work for everyone in the community edition? Great. Okay, so let's display our data. Each image has the true label, the label column. So let's print the schema. Training schema and test schema should be the same. So it has a label column, and then it has a features column, which is a vector. So let's just show this. So true is the default. So if you do show 3, it'll only show you like this. And show is the sort of standard Apache Spark command. It's sort of notebook free. It'll also work on command line and Spark shell. And yeah, so you see the label is 5, and then there's this feature thing, which says 780, and then it has all these integers, right? So, and then here is my, so if I use the Databricks display utility, it's a little more convenient. Oh, also, like, you can just change this to false, and it's going to get a bit ASCII text heavy, but you can see it without display, right? So yeah, so as you see, the second column has this vector. First index is 780. That's the length of the array that's about to come at you, and then these are the actual elements in the array. So I think 780. What is the square root of 780? Maybe. No, it's probably a rectangular array, I think. So we'll figure it out. So it's doing the usual, the images like this, it's doing the usual 1D indexing of a 2D array, right? So there are 780 pixels in this image.
27.93.
Okay, so it's not a square, so I think it's a rectangle. Good. That's a deep problem. Yeah, I used to be very good at arithmetic. I went to this weird military school in India. The children of the officers of the British Army went to a special school, but then they mixed it with the Upanishadic tradition. So they wake up early in the morning at 4 and boil the water for the children to take the shower at the right temperature before we took showers. We were 11, 12-year-olds, right? So anyway, it's a. So anyway, my point is, if I got the multiplication wrong, I had the option of using the class's ruler, which is the same ruler that was used to spank all these British kids in the late 1800s, or I had the freedom of going and fetching my own stick from the tree, because it was in the forest in the southern Ghats, in the mountains in South India. So anyway, I always got and fetched my own stick because I know the way the teachers hit and how quickly they move, so you can move your hand to not get hit. So yeah, so arithmetic mistakes are were very dangerous when I was 12. Yeah, it's a different time, right? I mean, they really needed the kids to be able to do tan thetas and sine thetas really fast, because it was coupled with sailing, and so math was actually okay. So here is basically a dive into what these things mean. So I think this might answer some of your questions. So it says the pixels are displaying the intensities, represented as features, and what we have are as a sparse vector. So here the size is 780, and then these are the indices that are non-zero, and 0 here encodes the white space, the pure white part. And so these are the values taken by the non-zero, non-sparse indices, right? So 152nd position is 3 pixel gray, and so on. yeah, so yeah, that's just what it's explaining. And then we're going to start training a decision tree, right? So here is, I mean, I really, when I put these links, especially to Databricks or machine learning programming guides, I think, you should get in there. And so, yeah, I actually have not touched 2.3. So, but we're all running things on 2.3. So this way, if things break, then we'll try and get into it in real time. But it's supposed to be backward compatible. So, and then this is the main concepts in ML pipelines. So this is another really good one to look at, and this guy as well. So here we have all these things like Gini impurity and various measures of entropy and variance. And so those who really know, taken proper machine learning course, and know about decision trees can roll their sleeves up and get into various different options that are already built in. Okay, so here I want to sort of get all these imports. I want the Apache Spark ML classification imports, and this is a Scala way of getting just both the decision tree classifier as well as the decision tree classification model. And then I need this thing called a string indexer. I'll come back to that. So it's in the features, ML features library. And then I also need this pipeline, right? So this is the nice thing about Spark. These fully scalable pipelines for machine learning. So then I'm going to do the string indexer thing. So remember our current label column actually has integer, right? The type int as its label. But I actually want it to be of type string because the classifier models expect the label to be of type string because there's no integer information. Well, remember in a classifier, there is no notion of distance between labels, right? So this is a strange example because the label itself is a number, but we want the number to be represented as a string because it's really just a classifier. It's a bit weird, but it's okay. So then all I have to do is I create my immutable val as an indexer, and I'm creating a new string indexer, and I set input column to be label because that's in the thing I'm about to hit with the string indexer. And I want to set the output column to be my index label. That's the new column it'll add for the transformation. So that's my indexer. Then I create my DTC, which is a decision tree classifier. And then I set my label column to be the index column. That's what it really needs, because by default, it'll look at a column called features in the input data frame, and it'll know that's the features you want. And then now I'm defining a val pipeline. So this is new pipeline called pipeline. And then I use this method called set stages. And in the set stages, I can give it an array that consists of all the transformations I want done. So I'm going to give it, in this array, I'm going to give it the indexer. So the data frame that comes in gets this indexer applied to it, a transformer, which means it'll add this new column called index label. And then I'm going to pass that to the next stage with this, which is my decision tree classifier, DTC. Right? So you build a pipeline. So now let's fit a model to our data. So this one basically is the same. It's so pipeline is done, and then the fit method will apply to the last thing. It's the decision tree model, and then we pump in the training data. So the training data goes through the pipeline, right? Indexer, DTC, and then the fit method is called on the DTC, what comes out of the pipeline. So that's now our model. Now our model, yeah. So now let's inspect what tree it has learned. This may take 30 seconds for you guys. I don't know. And then so I can do various things. So one thing I can do is model.stages, and then there is something called the last, which is the last in the thing in the stages, and I want that to be as instance of a decision tree classification model, right? So this is basically my fitted final tree. So if you examine this, it's taking feature 350, right? Which is what now? So you can look at this, right? I mean, this is 128, right? It's more than 128 or less than 128. So, and then if you look at all the features, are they all numbers less than the total number of elements in this 1D indexed array of the grayscale image?
Is it binary tree?
Yeah, this is a binary tree. I mean, decision trees are generally binary. That's not what I'm asking. I'm asking, so this feature is what? Is it? Yeah, it's a root node of the binary tree, but it's splitting on which coordinate, and what is the meaning of this coordinate?
It's like this center pixel.
Right, because how many columns are there in this vector? Because remember, each grayscale image is a long vector of 780 elements, right? So, in San Francisco example, we only had 7, right? Price and elevation. Now we have 780, so we're sort of looking at all of it. So this is splitting up the 350th index, whatever this means, okay, of all the images it's seen through. And then it's saying any grayscale value that's greater than 128, fork to the right, and anything less than 128, fork to the left. That's what's going on. It's just a display of that. And, so 1, 2, 3, 4, 5, sort of, I'm doing 5 splits. And, yeah. So you see, this is now the what do you call them? The handwritten digits for 1 fall in this final leaf node. The 4s fall here. 9s and 7s and 8, 6, so it kind of, see there's a 4, 7 here and a 4, 7 here. If you probably really dive into it, that's like slightly similar ways of writing 4 7s and 1 4s. I mean, it's just, so now as, so the tree makes predictions. So now we can classify a new example, right? The tree starts at the root node, and then we basically chase the pixel values going left or right, and then finally the leaf nodes tell you what image it is. Of course, it's doing all these things under the hood, right? It's using it's a measure of default measure of purity index, and it's looking at every possible, all possible 780 dimensions. Where should I split? Which of this 780 dimensions should I split, and where I should split to maximize the purity scores in each cell at the first split. It's all of that is being done for you, right, under the hood. And it continues, it recurses. So this is hyperparameter tuning. So I try to use the lingo from Wikipedia that has the most community support. So a lot of people call this hyperparameter optimization. So we want to choose these optimal hyperparameters, and the standard approaches are, we'll get into this thing called cross-validation, where you hold out a bit more of the data called the validation data. You don't let the training algorithm, the fit method is only applied to the training data, and you keep a bigger chunk of data, you hold it out, and then you break that into 2 chunks, the validation data and then the test data. And use the validation data to do hyperparameter tuning. It's kind of the basic idea. There are many approaches. I think we'll just do a simple grid search. We'll just have a bunch of hyperparameters. Okay, so what we're going to explore is the maximum depth. I said this is the most primitive, one of the most basic ones to control the complexity of the tree. So what am I doing? I'm just saying let val varied max depths models be this thing. So in Scala 0 until 8 will give me a loop. of integers from 0 to 8. And then I have this map I'm doing to each of those integers. What I'm doing in the map, here's my little block of code. I take whatever comes out of this. So initially it'll be 0, then 1, and so on. I call that max depth. Okay, and then I map that to all of this. So I take my DTC model. Remember, it's all well defined above. Right? So I set the max depth parameter to this I call the set max depth method, and give it this max depth parameter that's coming in. So this will change. And then I call my I have a fresh pipeline inside, and this pipeline uses my set stages, and it calls my array indexer and DTC. And this is kind of the beauty. So now I can take my pipeline and I can do a grid search using a simple for loop, right? And all of this, so wherever parallelism is possible, a lot of this is taken care of for you. And then for each of these models, each of these maximal depths, I do a fit with my training data. Right? And that's what's going to get returned, right? Because this is classical Scala block. So whatever is the last thing will get returned. That's what I'm calling this. So this will be some kind of an array of models that have been fitted to training data with various max steps. This will take a little more time. So as that's running, let's look into this thing called the F1 score, because we need some metric to evaluate the performance of our classifier. So in binary classification, the F1 score, or the F score of measure, is used to measure a test's accuracy. So it considers these things called precision P and recall R of the test to compute the score P. The number of correct positive results divided by the number of all positive results returned by the classifier, and R is the number of correct positive results divided by the number of all relevant samples. So F1 score is the harmonic average of precision and recall. So this is like one metric. We don't want to get into Warsaw metrics. It's not worth it. So it'll tell you something. So if this if the F1 score reaches its best value at 1, it's perfect precision and recall, and its worst value at 0. It's all we kind of want to take from this for now. Right? So it's well defined metric. So then let's see. Did you guys' pipeline finish? How many seconds did it take on the community?
90 seconds.
Okay, so it's academic cluster is only like not that much powerful. So then this one is So now I'm going to import Spark ML evaluation methods from the ML library, and in particular I'm interested in bringing in this multi-class classification evaluator. Okay, so if you do logistic regression, it's only binary, so you will do a slightly different evaluator, but all these evaluators are abstracted and defined in a nice way for various classes of machine learning algorithms. So then I define my my immutable evaluator, and it's just an instance of a new multi-classification evaluator where I set the label column to be my index label, because that's what I've done before. And then I want my metric name to be set to be F1. Okay, so that's my evaluator ready to go. So now what I'm going to do is I'm going to do F1 metric performance measures, right? And all I'm doing is the same thing. Max depth gets pumped in. I do my predictions, and but now you see I take my model, hit it with the transform method, and then I put in the test data. Remember, I held out the test data at the very beginning. So that's going to be pumped in, and this will actually create predictions. So now I want to do my, I want to return a tuple, like a, so the tuple's first element will be max depth. So I want to know what the max depth was. And then I want my evaluator I just defined to be used on this method called evaluate, and I throw the predictions that I just did at it. Okay, so this is basically, it should give me the F1 score as an extra column now, done on the test data. Yeah. So I know my maximal depth, and then I can just use the show method. So now I know how the F1 scores are. Remember, if F1 score is 1, it's like perfect prediction. So the F1 scores are, kind of increasing, right? So as the depth increases, I mean, zero depth is like, not doing much, right? So depth 1, is the one split, so with depth, as expected, the F1 score is improving. All right, so now, so even though the deeper trees are more powerful, they're not always better, right? So the other big problem is, training will take longer and longer with larger max depth parameter as well. And of course, we have this whole problem of overfitting. So now we bring in the third part, right? So we're going to hold out some of the data and use this held out data to decide on the optimal depth. And then we'll still use the test data to test it. Right? So this is a sort of generic way to control the generalization error. So, so here is the other hyperparameter called max bins. This is a way of discretizing the data. Right? So what this it explores a sort of more low-level setting. I will let you guys dive into it, but it essentially discretizes or bins the gray values instead of the native scale that it comes in. It will sort of coarsen it. Okay, and so I can control this sort of coarsening using the max bins parameter. So if we set max bins equal to, then we are effectively making it a black and white image. Call. So well, maybe that's enough for handwritten digit recognition, right? And so yeah, the next cell takes about 35 seconds. So it's training several trees, and then you can, it's running. We can look at the max bins thing in detail if you want. So what's going on here? So we have, so I set my max depths to be 6, just because I don't want to stand here for 4 or 5 minutes. You can do a grid on both as well. So now for that fixed max depth, I'm going to try to play with the max bins. So I'm doing the same. I take my sequence. So 2 is black and white, 4 is, 4 gray levels and so on. And then I'm just doing exactly the same thing. And if you notice, all I'm changing here is set max bins to be whatever max bins is coming in the loop, right? And I have my same pipeline. I have to fit to the training data, create my model, and then I put my test data into the transform method of the model, and I call my evaluator. So let's see how this looks. So here, this is interesting, right? What do you guys take away from this? In black and white, is that enough for this problem? At least at max depth 6 is black and white enough. Yeah, right? Because you see, the F1 score is 0.74. It's in fact better than having 4 gray levels. We don't want to split too much, but if you zoom out, it's about 3/4, right? So, and this is way faster. So, in some sense, it makes a lot of sense, because why do you need that many coordinates to just have a black and white image represented in grayscale to come back to? So this is not, it's making a lot of sense. Yeah, it hurts performance only a bit, but I think I wrote that one. So now it seems to be better than this one. This is just it's probably just I'm not controlling the seed, so the pseudo-random number generator. So it's just pseudo-random choices for, I don't know. So anyway, now
quick question. Yeah. When we do this hyperparameter tuning and we go from 0 depth to 8, a tree of 0 depth, how would that look like? I mean,
Yeah, so I think what you this is so what you really want to do is to do two loops. I mean, if you want to explore both of these hyperparameters simultaneously, I would do two loops. But I think you'll waste electricity in this example because black and white is enough just from intuition and a
Yes, yeah, but I mean for the depth, if you have depth of 0, what kind of tree is that?
That's not that's just randomly shooting. You know, there's nothing going on. You put everything and say, yeah, that was just done for pedagogical reasons. Yeah, so good. I mean, it's something, right? Yeah, I should make it 1. But it's also interesting, right? With 0, it says something. So what's next? So you know, we can try out tuning other parameters of the trees, and which you know you can spend like days doing this. I wouldn't recommend, but it's worthwhile chasing those pointers to find out what the knobs are for decision trees. Decision trees are like the first baby step. They're like this tree thingy, right? But there are more interesting things called random forests and gradient boosted regression, gradient boosted trees and things like this, where now you have, these are generally called ensemble methods. So now you don't have just one tree to do your prediction, but you have a set of trees or a forest, and then you actually combine information from all these trees somehow. And that's essentially the idea of an ensemble method. I don't know, Tilo might know a lot more about all the lingo. Is this called weak learners? And I don't know, something. Maybe we shouldn't go there. The trees are called weak learners. Yeah.
I mean, this was a big thing in machine learning theory, or I don't know, but years ago, whether you can combine a lot of very bad estimates into one good estimate.
Yeah.
I think the gradient boosted.
Yeah. 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 So I think what's the plan? Yeah. So I don't know if I have included this, but I think you know it's not that difficult to jump into random forests and gradient boosted trees, at least syntactically and conceptually from where we are. And you know these are not these are very powerful methods. You should try them before you do anything too fancy on your own. They're implemented. They're fully scalable. They come with this full pipeline. It's cross-validatable. Blah blah blah. So let's see what's next in the. Oh right. So I have a question. Like, who is? I guess this won't know. So you know, people that are taking the geospatial module, who are not taking the. So okay. So So is anyone here planning to take the geospatial module? Okay, so that's great. So I think I kind of changed things around because I thought Simon might like some of these things because stuff Simon's doing is all in this framework. You can do hardcore data science with very little effort because you have everything set up. And then in the afternoon, or actually even now, we'll get into Twitter streaming and Scala and stuff. So all of this interoperates with machine learning libraries and pipelines. So here's my current record. And so people who are doing social media and big data, geospatial and big data, but not doing this. Yeah, so then we'll have to figure out something, but most people are. Like there's one person here, KTH math PhD student, but yeah, I don't know. Anyway, I slightly changed things because you know I thought it'll be stupid to like get into natural language processing or even give you T-sets into NLP without making sure you understand like in 90 minutes-ish basics of ML. So anyway, so this is kind of our next stop, right? So we have, this is the third library in Apache Spark we're about to get into. This is the third main one, right? And this is kind of legacy already. So so the latest one is called structured streaming, and I did cover this in detail in my course last semester. But Spark streaming is enough for our goals today. And let's see if our collector is still running. It's still running 8.45285. Let's see, 8.46. So yeah, slowly collecting more and more. data. So this is all done with the legacy Spark streaming, and it's enough to collect stably. And I'm hoping to continue this for 9 months. So, but if you want to do more fancy things, so I don't like stream to stream join. So you have like 2 infinite streams coming at you, and you want to do some machine learning or live on them. And the machine learning model that you've created would have been fitted from the historical data that lives in your data lake or whatever. And then that fitted model can be applied as a transformer on the live stream. And there are current ways of actually abstracting how you update the historical model live on the live stream. And you can fuse it with other streams, right? So this is not possible in what I'm about to get into, Spark streaming. That's the old model. And it's even more beautiful than that. You can not only do stream-to-stream joins with live machine learning updates from historical information, but do live SQL joins on the historical data to interactively explore and do live A/B tuning, right? I mean, this is, I was interviewed at Netflix, but I came to Sweden and I was about to leave New Zealand. There, it was an A/B testing job. And it's a very high salary, but, yeah, you have to basically do better than the guy who did the shift before you in your A/B testing and keep improving the performance, right? So it's ideal for this. And in fact, for the visualizations, at least in the Apache Spark summits, the standard things with ggplot, all of that is not going to work unless you have a big team working on your own customized D3 interactive visualizations. The nicer way to go is something called Vegas. So I don't think we'll get into this here. Although when we try it, Vegas, the matplot lib for Spark. So these are guys from Netflix that talk about this, right? Missing matplotlib for Spark. That's already old, but it's a continuous project. So I don't fully understand the architecture here, but they allow you to do explorations of sample sizes that are much more than what I'm doing here, right? When I just take a tiny fraction and see it in ggplot. Anyway, that's just an extra point. So what is the main idea? Spark streaming is based on, we'll do this RDD-based Spark streaming. And you can get into the Spark streaming programming guide here. Okay, so this is basically, and I think I just basically go through the programming guide here. So, and this is the latest one, right? So we won't do that here. So Spark streaming is an extension of the core Spark API that enables scalable, high-throughput, fault-tolerant stream processing of live data streams. And it can ingest data from many sources. So there's a whole ecosystem around Apache Spark and Hadoop and so on. It can ingest data from Kafka, Apache Kafka. What is this? Fault-tolerant queue something. The distributed streaming platform. What exactly does that mean? All right, knock yourself out. But the point is, it's highly integratable with your existing stack. Okay, so there's Flume, and so we will do Twitter streaming and REST APIs in our stuff this afternoon. Yeah, there's some typo someone spotted out in one of my homework assignments. This is not intentional. Yeah. I call Amazon Redshift instead of Redshift, but that's another thing. Okay, so you can just directly get in stuff from sockets and so on. So what's the main idea is that whatever your source is, you can do Spark streaming, and then you can do some processing and write it to your distributed file system, or some kind of online dashboard that sends alerts and things like this. So yeah, so internally it works as follows. So we have Spark streaming. It receives input streams, and then what it does is break it into batches of input data. These are small batches. So in some sense, it's like the classical RDD, except there the batch size is huge. Here, this is a micro batches. So it's a very simple notion of streaming in some sense. Then it sort of gets processed by the usual Spark engine, and then you get batches of processed data back. Okay, so it's a high-level abstraction called discretized stream or D-stream. So it represents a continuous stream of data, and yeah, so D-stream is represented as a sequence of RDDs, right? So you already know about resilient distributed data sets, and this is just a sequence of little RDDs. And of course, this is not ideal for real-time fintech applications where you do like algorithmic trading in sort of millisecond resolution. It's not what you want to use. There are other platforms for that. So they call this is near real-time micro batch stream processing engine, as opposed to Apache Storm, which originally heavily developed by Twitter. That's a real-time system. Okay, I mean, real-time. What is real-time now, right? I mean, the stuff. I went to Google Cloud Summit in Stockholm, and I don't know, they're doing some amazing things, right? Did I tell you guys about this? So Google has these cloud centers, data centers all over the world, and they have atomic clocks in some of them that are geospatially very far away. And then they use interval arithmetic. So they enclose real time up to atomic clock precision in an interval. And then they use these interval enclosures to do some their big table and things like this. So they are, so I think kind of CockroachDB is the one that's sort of the open source. I don't know who's really behind CockroachDB. I just want to point this out because what I'm teaching is like already 2016 stuff, right? So, so this is this is essentially the open source variant of Google's latest big table technologies. So there it's not NoSQL anymore. You can do like proper transactions in real time on completely large data sets, and you can write to your database and all of this. And I haven't dived into it, but I know I don't know that. Yeah, by the way, that's a good habit to know what you don't know and kind of, anyway. So this is relatively simple stuff. Okay, so now let's get into how do we. So we're going to do a hello world example of Spark streaming. So it's going to just count words on 1 second batches of the streaming data. It's going to use an in-memory string generator as a dummy source for streaming data. Okay, and here are the configurations that control the streaming app in the notebook. So we first want to make sure, can I do this? Right, so let me check and be nice to my colleagues. So I want to make sure that, because a lot of people running stuff from all over the world here. These are the libraries, these are the notebooks. Okay, there's no one doing anything, I think. So then what I need to make sure is I go to the Spark UI and then make sure someone isn't running some streaming job I'm about to kill. So there's nothing called streaming running. Remember, this is the Uppsala shard. In Uppsala shard, there is a streaming, that's running. So why I wanted to do that is to be considerate to other people in this academic shard, and before I kill some streaming job. But for you guys, it doesn't matter, right? Because you're your own bosses in your own community edition. So so I want to stop active context to be set to true, and batch interval seconds to be 1, events per second to be 1,000, and then yeah. So I want to make sure I know I'm on a more than 1.4 Spark cluster. So, but that's just a paranoid check because this was not available before that. So then imports. So we do our just everything from Spark, storage, streaming, and then this is our discretized streams again. So now we do a little bit low level. So these streams are, remember, sequences of RDDs basically, or discrete streams. So this is RDD at time 1, and it has data from time 0 to time 1, and this is RDD at time 2, data from time 1 to time 2, and so on. That's just it. So we just use time clock time to partition. So then this is how to define the function that sets up the streaming context for us, because it's just a hello world thing. So this thing is going to be, we're going to define something called a custom receiver as the dummy source. And I said there's no need to really understand this, so let's do that in the interest of lunch. So dummy source, basically, it's implemented as a custom receiver, and you know, it's a case, you know, it's a class. It extends this thing called the receiver string, storage level, memory, and disk 2. Doesn't matter. So it's going to, you know, it has an on-start method and an on-stop method and a receive method, and so it's going to be like our hello world string generator. Okay, so and then when we move into Twitter, we'll just, you know, tap into the public streams. So. So now we can do transforming and acting on the D streams is exactly the same idea, right? So we can do flat maps and get the lines and basically get a word stream. That's kind of what we're going to do. So lines are being thrown at us at different time intervals, and then we're going to do a flat map operation where we split by white space, and then we will get words D stream, and that's basically the first step. And then, yeah, so these are standard RDD operations. So let's see what's going on here. So to understand the creating function, you know, which basically creates a new streaming context, and it sets up our word count and registering it as a temp table for each batch of 1,000 lines per second in the stream. So what? So here's my creating function. So it gives me back a streaming context, a Spark streaming context. And so that's what I'm creating here. First, I do SSE for Spark streaming context. So I take an instance, you know, a new streaming context, and I pass into it the Spark context that exists. Okay, so you need to create the Spark streaming context from the Spark context. And then what I'm doing is I use this type seconds, so it tells me it's in units of seconds and it's batch interval seconds. So remember, we set this to be 1 earlier, right? Do you guys agree? Okay, so yeah, so then that tells me the unit of time at which it's going to create my streaming context. Then we create a stream that generates 1,000 lines per second. So that's this receiver stream. And remember, I said forget about what's going on, this dummy source thing we did upstairs. That's the thing that's going to take the events per second and create my dummy source. So I have a receiver stream ready for me, examples. So now these sentences are coming at me, right, with some random integer changes. And then I'm going to get my word stream, which is nothing but take the stream that we've just made. And then I flat map, I split by white space, and then I do word count stream, which is the word stream mapped where each word becomes a tuple with word comma 1. This will be, you know, type inferred as integer 1, and then I reduce by key. So word count, right? That's what we did last. But all of that is happening in the stream now. So then I create a temp table at every batch interval. So here I use this method called for each RDD. Right, because I have a sequence of RDDs coming at me in the word count stream. And what I do, I take each RDD in this word count stream, and then I convert to a data frame, and I give the data frame the column labels word and count, and then I do create or replace temp view. So that means, you know, I'm going to keep updating my HiveQL table live with my batch word count as a name. Then I basically go back to my stream for each RDD. I do a you know, system out print ln, so I keep track of what's happening as the stream's processing. That's that, and then yeah. So this is just some other details on making sure it waits until it starts. And so now we've created the function called create new streaming context. So why I kind of want to go through this is because when I've presented you with the experimental design for using the same discrete streams after lunch, you will understand this function I'm throwing at you. It's not hidden too much, so it's customizable. But it uses Twitter 4J, so via Scala. So it uses a standard Twitter library for this. And so now I want to start my streaming job. So for this, I have to stop existing streaming context, if any, and start or restart the new one. You cannot typically run multiple streaming contexts in a cluster, right? In a single cluster. So then that's all I'm doing here. If stop active context, then I mean, I'm a little paranoid. I want to go through each active streaming context and make sure it's all stopped. Okay, that's what this loop is. And then get or create a streaming context. This is just you know, well, SSC streaming. So now I'm going to create my my streaming context, SSC, and then if my new context created, then I say, oh, new context created, else, okay. And then I start my my streaming context, right? And so this should just work.
This job will produce 1,000 streams per second?
Yeah, so it's producing 1,000 of those sentences per second, right? I'm a dummy source 2, I'm a dummy source 6, I'm a dummy source 1, I'm a dummy source 0. So that's what's coming out. Right. So now we can do interactive querying, right? So I'm basically, because I remember I wrote this all word count to the table, so I know word 0 is occurring 93 times. So if I keep refreshing this table or hitting the same cell, I will get different numbers, right? Yeah. So anyway, you should try it quickly, because and then the main thing is when you're done, you want to stop it. Okay. Oh yeah, right. So yeah, so let me do this again, because I want to show you guys the Spark UI for streaming. Right. So let's see, that's running. This is why you need a dashboard, So what you want to do is go here, or go to the clusters, and if you go to Spark UI, there should be streaming icon, and so it's sort of telling you how many records per second are being processed and how many completed, and that's what I'm showing you in Twitter right here. It's just the same exact idea. It's just records per second are tweets. Okay, so this is like you are the boss. Like you can do this for. I mean, after lunch we will see how to do this on Twitter. It's exactly the same idea. So every single important piece of code is there. So how are people feeling? Good. Hungry? Yeah. 15 minutes, Oh, we can quit early, but if I here's the plan anyway. Let's kind of make a plan, right? Like, I don't know, kind of, yeah. So what I've basically planned to do next is, yeah. So I want to kind of throw you in the deep end of SQL on Twitter. So we started extending this Spark streaming Twitter utils in Apache Spark. It's not in Apache Spark anymore. It used to be, but we've been kind of expanding on it slowly. So I'll give you an overview of this, and we will actually, because this is a bit delicate, so I don't want you guys to like copy paste and hit cells. So they're all like confiscated in the 025_A and 025_B. So this is the tweet transmission tree stuff I was telling you about yesterday, that this whole US election hate group thing is built on. So here's the full-blown, this is what I mean by legally explicit, resolution. All the measurable maps from the raw tweets are, can be, held accountable. Because it's so these things I think are there. I'll tell you what they're kind of doing. We'll see them in action. And This is something Olaf and I might do, depending on this Olaf here. We'll see. This is like last night thing. So, but at least Olaf will try to show. So he's a candidate student doing his doing some project with me. He's got 10 weeks. So he's taking the course as well and learning Scala. And so anyway, we thought we can try to explore one particular user's timeline. Like, of course, one of my favorite ones is real Donald Trump. So we can and you guys can have, get your consumer key, consumer secret, token secret. If we get this in the next 10 minutes, it'll be really awesome. Then we can just go full on after lunch. So, Simon's video was there. In fact, Simon can step up and show this, which will be great. So then if you guys get these 4 keys and store them as a text, in some text file, then you can copy paste into here later. And then, we can, my Twitter handle, it's also verified, is at Razozone. This is at Real Donald Trump, so we can get Trump's recent history of tweets. And then I thought we could just, I'll show you, how to do some basic REST API and get the stuff. And then maybe Olaf could show how to kind of do this in D3. But we'll do this last because, I kind of want you guys to... So my main plan was to jump here after lunch. So this is the tweet collector, so how to capture live tweets. And those notebooks I showed you, we can just abstract them and just run these cells, because I'm just calling everything in that notebook by this %run command. So it's okay. You can descend into them later. So then we will, once we get our Twitter credentials, you guys can start doing your own streaming jobs. And we will start collecting the global Twitter free thing. What is that? It's not the Firehose. It's the free streaming API. So you can look at the entire planet's tweets to 1%. So it'll be quite a lot. So we can, start doing this, and then we will customize this slowly. Meaning, we'll sort of look into how to do capture live tweets by tracking a list of strings or following a list of users, or both. This is basically my elementary design. It's the most primitive design in, mixing both in the streaming world. And then, so this is, and then this is just like when you want to do your own live hashtag count. It's similar to that word count thing we did, so we can sort of process stuff on the live thing. And I hope that'll be enough for 90 minutes, right? And then let's see how things go. Depending on when Simon flies out, I can do the latent directly allocation in the, in the first part of the last 90 minutes. And I also have this Old Bailey Online thing, which is XML, because we're overly Twitter focused, mainly because Simon and I were kind of into it. But there is a whole world of digital humanities. In King's College London, I did some workshops there at one point. And so we can kind of get into this a tiny bit. This is XML processing. So this is very, very important for digital history and digital humanities in general. And I won't get into the paper because you guys need to know quite a lot about Bayesian non-parametric statistics before you can understand the models in that paper. But at least we will maybe flex our XML muscles if time permits. So yeah, and let's see how things go. Maybe yeah. So maybe it'll go really fast, and Mariama can just tell us like what she did on top of article topics and retweet networks, right? This is LDA thrown on top. So this is really a 2-day thing, but then we spent so much time on like context and law and introduction, which is important as well. So it's sort of, I leave all the videos there. So if you guys want to knock yourself out, you can, but I'll make sure you have the foundations. Does that sound like a plan? Yeah. So Twitter, like how do we get Twitter credentials? So I do this, developer.twitter, is this the one? Developer.twitter. Does everyone have a Twitter account? Okay, so I can't always remember. So is it dev.twitter.com?
We've got apps.
Apps.twitter.com.
Oh, okay, thanks.
I think for Facebook it's dev.
Okay. Yeah. Okay, so once you have a Twitter account, then you should come to apps.twitter.com, and then you can create. So I think this is my public one that I use for everything I'm doing. It's called Meme Streamer. So I have this one called STS22 Demo for Teaching. So you would create a new app, okay, so like that, and then you can put your name, whatever. I'll call myself Razboy, right, because I'm assisting myself. So. I don't know. Yeah. So, I mean, you can just, don't put my website, well, I don't care, but, you can just put whatever. You don't need callback URL. We're not doing any kind of real interactions. It's mostly observational. Yeah, this I really can't insist any more strongly. You really need to read this, or at least, yeah, read it. Yeah, this is why I can't show you my experiments I've done in detail in these other shards, because I just think Trump will like me enough not to let me, I mean, because I'm showing what he's publicly posting in the last 300 tweets, right? I'm just sharing it. But Twitter doesn't want you to let people download the tweets directly from you. So there's this tiny technicality that if I make my Databricks notebook public, then if you do the download CSV in my display data frame, those tweets are coming from you, right? But then my way around that is I'm saying you put your XXX there and you will get the next thing. I mean, so it's, but I'm not too worried about that. And but for the class, I thought you guys should kind of see this, and I can delete that table in the end too. So then I say, okay, yes, I've read this, and create your Twitter application. And error, failed verification. Oh, it's already taken, right? Yeah, so it shouldn't happen for you, right? So, okay, so I have my own thing I've already made, so I'm going to use that. Okay, so did everyone successfully create this?
Yeah.
And then, so I think this one is my usual one for this demo stuff. Yeah, so here yeah.
Sorry, what was the website?
apps.twitter.com. Apps.twitter.com.
Oh, yeah, but like within this.
Well, do you have a website? Your own website?
No, but no.
Then I think you can leave it empty, is what Simon said.
I think you need to enter something, and I think
Yeah.
you need to enter something starting with HTTP, not just the www. But you can.
But don't you study here in some department? Don't you have a department webpage?
Yeah, I guess.
Yeah, I don't know. I mean, it's like some automatic.
I usually make something up.
Yeah.
As long as it's formatted as a WordPress. Like 123.com.
Yeah, we're live, So yeah, that's the guy. No, I mean, just put some valid URL. You don't. You can make a Google Sites for it really quickly. I mean, so what we really want is let's see. So if we go here, then is it keys and access tokens, Simon?
Yeah, I think it is, because you need to generate the two
yeah.
extra. If you scroll down,
yeah.
You have a button to. No, these are all of them. Yeah.
Yeah,
you have 4.
Yeah, I already generated it, but I think Simon's video shows, because I can't redo this, because I.
Yeah, because I think you get 2 of them. You need to press a button to get the 2, the 3rd and the 4th.
Yeah.
Twitter 4J example.
So yeah, if you I'm going to test my OAuth thing settings. I don't know if it seems to work. So anyway, so you'll get four things, right? Just save them into a text file, and if you haven't been able to do it, please get some help from your neighbors or raise your hand, or I'll be here a little bit before 1:30. So.
Så får jag en crash att biblioteken installera det eller importera det.
Då är det där skala eller bibliotek?
Måste vara skala bibliotek.
So are there any questions?
Yes, how do we import or install the Twitter4j examples?
Oh, I will explain all that.
Oh yeah, okay. Cool.
Yeah, so there's a lot going on. I have to show you how to import libraries, the right, we'll do Maven coordinates, all that. Yeah.
Oh, you're just
Yeah, also it's
och sen på den här dropdown meny.
Ja.
När du ska göra create notebook så kan du istället köra create library. Det är library som kan vara jag har bara gjort det med
Libraries are here. Just det.
då måste man
Kan man säkert plocka ner den. Nice. Publisher tools.
Ja, jag ska inte det. Jag tyckte så.
Var det bättre? Var det bra? Jag tyckte det var bra. Vad hade du haft för det?
Men det är mysigt.
Det är mysigare än